Hi everyone, so I guess everyone can hear me. So we'll start within 5 minutes or so. Yeah, so we'll start with today's session. So as you all know, this is the problem solving session. Just a second. I guess everyone can hear me. Yeah, so this is the problem solving session week 3 of the course titled as Semiconductor Devices and Circuits. And this is a brief introduction about me. So my name is Shomnath Bhattacharjee and I am pursuing my PhD in Department of Electrical Engineering in IIT Jodhpur, and my research interests are towards flexible and organic transistors, that is, especially towards thin film transistors for like implementation of them in neuromorphic devices. And previously, I have done my MSc in electronics, while I have done also my BSc with honors in physics. And the regular schedule of this course, like problem solving session, is on every Sunday from 7 to 9. And this is the basic course layout. So like this is a 12-week course, as we all know. So the first week we have learned about the excursion in quantum mechanics, where we have solved the Schrodinger equation in different conditions and those things. Then we have moved towards the excursion in solid state physics. We have learned the basics of solid state physics and those things, the basic crystals and those things. Now in this week we'll learn about the density of states, Fermi function, and doping. So this is our today's class, and so the basic thing of this points, as it is certain from the title as well. So there are three parts, three entire parts. That is the density of states. What is density of states, and how are we implementing it on like different dimensions of materials, and also Fermi function. What is Fermi function? What is the Fermi level in a semiconductor, and those things. And towards the end we'll move towards doping. So what is the doping concentration, what is the carrier concentration in intrinsic semiconductors, and how are they changed after doping a certain impurity in this intrinsic semiconductors, and ultimately making them an extrinsic semiconductor. What are the degenerately doped semiconductors and those things. So we'll move towards the basic introduction to all the topics we have learned this week, and then afterwards we'll solve few simple problems, and by through the utilization of those problems we'll move towards understanding these concepts more intensely. So the first concept we have learned this week was density of states, or the DOS. So there is density of states. So what is the density of states? It is nothing but number of available states per unit energy per unit volume at a fixed energy level. So this is the basic definition of an density of states. So density of states is exactly the density of available states. That is number of available states per unit energy per unit volume, and it is also at a fixed energy level. So we write it as n of e or g of e in many cases, but let's say n of e, and it is proportional to e to the power half. We can write the value as n of e equals to 2m cube whole to the power half e to the power half divided by pi square h cut cube. So this is the basic value of density states, and this is for 3D materials, so like silicon and those things. Now, to understand this kind of a density of states, so this is energy, while let's say it's DOS. Sorry, DOS. Now, here, if we want to plot this function for the 3D materials, what happens is that whenever there are three different values of this energy, whereas the first one is the case where the energy is in between the values of, it's less than the values of EC, and we can write it as like this. So this is the value of EC, that is the value of the conduction band, energy value of the conduction band, and EV is it's not visible. um just a second. Just a second, right? Should I remove it and back? Yeah, is it visible now?
Yes, sir, visible.
Okay, fine. Yeah, so I was saying that the energy levels can be in three of the separate ranges. So the first range can be if it's in between these values, the EC value and the EV value. That is, let's use a different color maybe. If it stays between these value, that is the EC and EV, that is if it's less than EC while it's also greater than EV, the value of energy is zero. This is the forbidden energy band gap, forbidden energy states or forbidden energy band gap. In the second case, it can be more than the value of EC, which is like let's say this, while also less than infinite. So in this case, what happens that the value looks like this, and it takes the value of this 2m whole to the power half, but it's the difference between E minus EC whole to the power half, as E is greater than, just a second, I mistakenly wrote like this, I mistake. So it should be like this. E should be greater than the EC values. So EC, so this would be like this, pi square h cut cube. Whereas the third case, and for this case the value will be like this, and the third case where the value of E is less than EV, so in that case it will look like this, equals to or less than. So inclusively, the states will be in this region. So the value would be 2m cube whole to the power half EV minus E, as EV is greater than this, minus half whole h cut cube. So this is the third state. There are three different cases where energy can take up like three different values. Now, so this is for the 3D materials. So what if there is a material that is in two dimension, where a single dimension is very much smaller than the other two dimensions. So in case of like 2D materials, in case of 2D materials, so these values, like in case of right, yes, the definition also changes a bit, because in this case we have like ascertained that it is the number of available states per unit energy per unit volume, whereas in 2D materials it would be number of available states per unit energy, that remains the exact same, but this would be unit area, and the value we get from this is Ne equals to m by pi h cut square. So the thing to remember in this case, that is a special note, is that it is independent of E. There is no E term here, so it is completely independent of this. While in this case, there was three different cases based on the energy levels. So if it's less than EC while greater than EV, if it's greater than EV, and if it's greater than EC as well. So based on these structures, we have like three different states where there are few forbidden areas where the electron stays inside the conduction band, whereas the electron stays in the valence band. But in case of 2D materials, there is no separate cases, as there is no no dependency on the energy values. So the next one is 1D material. That is, in that case, two of the other dimensions, like in 2D there was a single dimension that was really like negligible in values, like with respect to the other two dimensions, whereas in 1D material there is only a significant single dimension. So the value of any in this case comes out to be m to the power half e to the power half 2 to the power half h cut pi. So in this case there is again dependency on dependency on energy values, and the dependency is of e to the power of minus half. And for 0D materials, the value of n is nothing but energy state. So this is the basic concept we have learned from this. Then next we have learned the basic concept of Fermi function. So what is a Fermi function? Fermi function is basically the probability of finding an energy state at E energy level occupied by an electron. So it is nothing but if there is an energy level, let's write it like this. So if there is an energy level called E, so the probability of finding the electron in this energy state is called, so if the probability of finding this is Fe, let's say, so probability of finding this electron in the E energy state is called the Fermi function, or the probability to finding this is called like is defined by the Fermi function. So we can write it as like this: Fe is 1 by 1 plus e to the power of E minus Ef by kT. So this is nothing but Fermi-Dirac distribution. This is the basic Fermi-Dirac distribution, and here the value of Ef is nothing but known as the Fermi level of a specific material or of a specific case. And apart from that, kT is the Boltzmann constant and everything is there. So there are specific cases in this case, like in definition of this Fermi function. So the first case is if, like let's say, E minus EF is much greater than the value of KT. That is, is it exceeds the value of Boltzmann constant. In that case, what would happen with Fe is that this number one, let's write it down first. So what happens here? So this number one becomes negligible. So we can write it as like this, not exactly like this. So let's write it like this. So E minus EF by KT. And the second case would be like, let's say, E minus EF is much less than KT. So what would happen that then in that case 1 minus Fe, so it is inverse of the like finding the like the probability of finding the electron in that energy state, that is so it is probability of not finding the electron in that energy state, that is the opposite of opposite of this. So it can be written as E of E minus EF by KT. So probability of not finding the electron in that energy state termed as E. So E is the energy state here, energy state. So probability of finding an electron within not within this energy state is the value of this. So these are two special cases we have to remember for like problems and those things. And we'll move towards the basics of carrier concentration. So we have already learned about the carrier concentration, but based on this like probabilities, that is the probability of finding the function, that is the Fermi function, and also based on the limit of ranges that we can find the energy states, we can like define this carrier concentration again. So carrier concentration, let's say so there are different carrier concentration in P and in I. So the Ni is the intrinsic carrier concentration. Ni is the intrinsic carrier concentration. In case of a, let's say, in a like a intrinsic semiconductor, so in an intrinsic semiconductor, the number of total electrons per unit volume in the conduction band is termed as N. So the carrier concentration, that is the number of total electrons in a unit volume in the conduction band, is known as N or termed as N. So we can write N is nothing but the energy values will be from infinite to EC, as we want to get the values from there: Fe, Ne, and De. So Fe is the function here directly, and Ne is the probability of finding that number of electrons in that. So it comes out to be Nc, Nc e to the power of minus Ec minus Ef divided by Kt. So we can write it as like this. So the carrier concentration for electrons to be able, the electrons in the conduction band is this, whereas similarly P, or the number of, we can write it like this maybe. So the total number of holes per unit volume in the valence band is termed as P. So this is the whole concentration, and we can integrate it on from minus infinite towards EV. So it's EV, and this is nothing but holes is 1 minus Fe. So this is, let's write it like this. If we can remove it like this, it will be also NEDE. So we can write it like this: P equals to NV of e to the power of EV minus EF divided by KT. So this is the whole concentration. Now, so we have got the values of N and P. So as this is an intrinsic semiconductor, let's write it on the next page, I guess. As this is an intrinsic semiconductor, as this is the intrinsic semiconductor, so the intrinsic carrier concentration, that is Ni, should be equals to N, that is the electron concentration, and also the hole concentration. So electron concentration, that is the number of electrons we have found in per volume we have found in conduction band, and the number of hole concentration that we have found in like the valence band should be equal. So we can also write it like this. So if we multiply Ni into Ni, then N into P. So we can write it like Ni square equals to Np. So this is also an important formula. And apart from that, we also know from this is that, let's write it again first. In Nce to the power of minus Ec minus Ef divided by Kt, and we have got P equals to Nv into e to the power of Ef, Ev minus EF divided by KT. So we have got already got this. So from the above equation, we can write it like this. So Ni square should be equals to N multiplied by P. So it should be Nc e to the power of minus Ec minus Ef divided by KT multiplied with this. So it should look like this. Now, if we multiply the total terms, it would look like this: minus EC minus EV divided by K, divided by KT. Now, the term here that EC minus EV is nothing but, what is that? Yeah, so EC minus EV is nothing but the forbidden energy band gap, that is EG. So we can write it like this, equals to NC into NV e to the power of minus EG divided by KT. So we can get the values of Ni equals to root over of NC NV e to the power of minus Eg by Kt. So from this, the main observation we have got that NC and V is constant numbers. So NC and NV both are constant values. Now we can get that Eg is also constant and the value of K is also constant. So from this we can get that if we keep the value of T as constant, so let's write it, if T is constant, then we can get the we can get the value of Ni as constant as well. So if there is no change in temperature in the intrinsic semiconductor, there is no change in intrinsic carrier concentration. So if we change the if we change the the temperature, the carrier concentration will change, but there won't be any change in the hole concentration and the electron concentration at that case. So now we'll move towards solving this again. So again we know that in this case n is equals to p, as we all know. So what will happen that we can write it like this: e minus of ec minus ef divided by kt is nothing but equals to nv e to the power of ev minus ef divided by kt. Now in intrinsic cases we can write it like this: intrinsic semiconductor, we can write the ef equals to EFI, that is the intrinsic let's write it down, I guess. So we can write it as intrinsic Fermi level. So when the semiconductor is intrinsic type, the Fermi level is termed as the intrinsic Fermi level, or we can write it as the Fermi level in a pure or intrinsic semiconductor. Okay, so from this we can get the value of this EFI as EC plus EV divided by 2. I'm not solving that, I'm just writing the formula here. So this would look like this: NV by NC. So based on this, we can also write that EFI equals to EC by 2 plus EV by 2 plus KT by 2 ln of MH star divided by ME star. Should have written like this. Yeah, that's fine. MH star divided by ME star, effective mass of hole divided by the effective mass of electron, whole to the power 3 by 2. So this is the basic formula we get for the intrinsic Fermi level. So we can easily determine the intrinsic Fermi level based on the values of EC, based on the values of EV, the effective mass of hole and effective mass of electron. Now uh, now we move towards so this is all the cases are here for the intrinsic semiconductors where there is no doping, there is no impurities in the semiconductor itself. So what we have done until now is that we have, based on the Fermi levels and the probability of finding an electron or hole in certain cases, like in hole or sorry, in conduction band or in valence band, we have equated the values of n and p. So based on that we have got the intrinsic carrier concentration, which is nearly a constant if there is no change in the temperature. Just a second. Yeah, sorry. So there is no change in temperature, based on there is no change on temperature, and we have calculated the value of intrinsic Fermi level, which is the basic Fermi level, but as this case is intrinsic, we are writing it as the intrinsic Fermi level. So we'll move towards the extrinsic semiconductors. So for that we need the concept of doping. So what is doping? Doping is when we add uh, like let's say if it's the case of like silicon, so uh, we add a molecule with 3 valence band electrons or 5 valence band electrons, that is trivalent molecules or pentavalent molecules. So these kind of a things are used as sorry. So these kind of a things are used as impurities. So to increase the let's say it like this. So doping is nothing but adding impurity in intrinsic slash pure semiconductors and making them unpure slash extrinsic semiconductor. Okay. So we are making an pure semiconductor, I like impure. So this impure semiconductors. Okay. So there are two types of doping. So based on the if we are using a trivalent molecule or an pentavalent molecule, so based on that there are two types of doping. So the first one is known as the N-type doping. So the main aim to if the main aim of ours is to increase the value of N, that is the number of electrons found per unit volume in the conduction band. So then the case is called the N-type doping. Or there are another case that is similarly, that is the P-type doping, whereas the main intent is to increase the whole concentration here. So and in this case the semiconductor is known as the N-type semiconductor, whereas in this case it is known as the P-type semiconductor. Okay. And so now what have happened that based on these dopings, the number of the concentration of N, that is the value of N, has increased in case of N type, and in case of P type the value of P has increased. So based on these facts we can say there are like two new terms, that is the acceptor concentration. So what is this acceptor concentration? Sorry, just a second. Yeah. So so based on this, first we will have the donor concentration. The donor concentration. So what is the donor concentration? That is written as ND. That is the donor concentration. So this is number of donor atoms per unit volume. Whereas we will also have the acceptor concentration, that is in A, or number of acceptor atoms per unit volume. So the basic units of these cases, the concentrations are written as this per cc or per centimeter cube. So now, so if let's say if there is a there is a semiconductor that in a semiconductor intrinsic semiconductor, it has like both type of doping. So if the doping is doping is more in the n type side, so the if the final semiconductor is n type, the dopant concentration would be nothing but Nd minus Na, because there are more donor atoms than the acceptor atoms. Whereas in case of if the final semiconductor is p type, will have the dopant concentration as this Na minus Nd, because Na is greater than Nd. So the basic thing with these kind of dopings are that we'll have the band changes. So what happens, so if we are saying this is an basic intrinsic semiconductor, the things look like this. So if this is the conduction band, whereas this is the valence band, and this is the intrinsic Fermi level. Okay, so intrinsic Fermi level, that's why we are writing it as EI. Now if we move towards, let's say, an N type, so what happens? Maybe I'll have to make this smaller. So in case of, so this is the basic case, this is EV, whereas this is the EI, this is EC for another semiconductor, and this is EV. So for each case, the EC, EV and the intrinsic levels are same. But here, in case of when there is doping, so these two are cases of different dopings. So in these cases, what happens, that it is termed as EF of I, and in this case as well, it is EF of I. That is the intrinsic Fermi level. And now, so there is a Fermi level difference. So if this, let's say it's an n-type semiconductor, what happens, that the Fermi level will shift towards the conduction band. This is termed as the EF, whereas the Fermi level in case of intrinsic one, it would be here. That is, the shift would be towards the valence band, and the intrinsic Fermi level band would be at the same in each of the cases. Okay, now, so apart from this, there are several special cases where if the like, let's say, the difference between the Fermi level and the conduction band is less than 3 kT in case of n type, whereas the difference between the Fermi level and the valence band is less than 3 kT in case of the p types. These kind of semiconductors are called the degenerately doped semiconductors. So basically the limit should be kT. So the basic, if like, let's say, no, with not this, so let's say like for the physical limit, we can say that it can be like this. So if these two are here, the basic difference is, let's say, kT. So the basic difference is kT, whereas like in case of like this can be called as a degenerately doped, whereas in these cases already, if the difference is only 3 kT, that is more than 3 kT, so we can say it as the degenerately doped based on the definitions. Now we have to understand what is the carrier concentration in this case of like extrinsic semiconductors. So the based on the doping concentration, we need to know the carrier concentration in this intrinsic semiconductors. Okay, So we know that the value of n is nc e to the power of minus ec minus ef of I by kt. So this was our first, not sorry, just a second, ef by kt. Okay, so this was our first equation. We have already solved this. Based on this, we can write it as n equals to nc e to the power of ec minus ei, that is the EFI, intrinsic level, kt, multiplied with e to the power of ef of I, no, sorry, e of f minus ef of I. So we can write it like this, right? Because no, it's fine, I guess. Just a second. Yeah, so we can divide the terms in these two terms, and based on this, we can write it as, so this term is nothing but ni e to the power of EF, that is the Fermi level right now, and EFI, that is the Fermi level when this was an intrinsic material. So the change in Fermi level multiplied the intrinsic carrier concentration. So right now the just a second, electron concentration is nothing but the multiplication between the change in the Fermi levels based on this, and also the intrinsic carrier concentration. Similarly, we can get the value of P, that is the intrinsic carrier concentration multiplied with E of EF minus EF of I divided by KT. Now, based on this, what we can write that if we multiply N into P, so we would get Ni square. Both terms will just, we can write it like this. So let's say if we have got NP, so we can get NC e to the power of minus EC minus EF divided by KT, and NV e to the power of minus EV minus EF by KT. In this case as well, we will find the value is nothing but Ni square. So even for like intrinsic semiconductors and also for the extrinsic semiconductors, we get the value of np equals to ni squared, that is the concentration of hole and concentration of electron is the multiplication of the concentration of these two things are equals to the intrinsic carrier concentration whole squared. Now finally, in this this week's lecture, what we have learned that the temperature dependence on ND, that is the donor concentration, in A, that is the acceptor concentration, and also all the carrier concentrations as well. So how the changing the temperature depends on this kind of a things, and based on that we have also like got that how the change in the effective mass of hole and the effective mass of electron on these concentrations as well. So this was the basic recap of this week's lectures. If anyone have any question, you can ask me right now. Otherwise, we'll move towards the problem solving session and those things. If anyone have any question on any of the topics or these things. In most of the cases, I have omitted the solving and those things because you can get it otherwise. So, but like I have just discussed the main topics here that we have learned through this week.
Sir, will you please explain the difference between non-degenerated semiconductor and degenerated semiconductors?
So the basic difference between them is that yeah, I have skipped that part. But in case of like degenerately doped semiconductors. The basic difference is that, like in the physical limit, as I was saying here, so in the physical limit, it should have been like EC minus of EF, that should be less than kT. The physical limit should have been this for the degenerately doped. But in case of like when the limit is EC minus EF less than 3 kT, it is already called a degenerately doped semiconductor. So a non-degenerately doped semiconductor is that a semiconductor where we have much higher carrier concentration. That is, the value of N is high and the value of P gets a little bit like lesser in that case. But in that case, what happens that if the semiconductor is like aptly doped, what happens that the carrier concentrations increase. So if we have, let's say, the value of N is 1 here, if we are doping it in a certain way, the value of N can be, let's say, 2, 3, and these kind of a things. But there is a certain limitation where we can increase this value of like, let's say, the electron concentration in n type cases. So in n type cases we can, let's say, increase, let me write this thing, I guess. Yeah. So as we are saying here, so in case of n type doping, we can, let's have a doping concentration of 10 to the power 10 per centimeter cube, like this. That is the n type doping. So what happens that based on this, let's change it like okay, so let's say it's like this. Okay, this is the donor doping. Based on this we can increase the amount of N, and based on this like we can increase the amount like much further. But there is still a limit that the N won't be, like N won't be drastically changed from the basic value it had. So based on that, if there is aptly doped, the semiconductor will increase its carrier concentration and the mobility and those things. It everything would increase based on this thing. But a degenerately doped semiconductor is like, even if you are doping the semiconductor upon a certain level, there is no, like, let's say, there is no significant change in the value of this concentration amounts. So this is the basic thing for the degenerately doped and non-degenerately doped semiconductors. And based on that, different phenomena changes. I have not like gone into details of those, that doping concentration in those cases and like the value in those cases. But like, so this is the basic, like from the, like the, let's say, the empirical changes we can see, but not the exactly the mathematical changes. So we have to learn about that otherwise. Any more questions, or like if you have got the answer or not?
Yes, sir. Yes, sir. Thank you.
Hmm. Um, if there are no questions, let's move on to the questions and those things, and then based on that we can get more like in-depth knowledge of this, like this what do I say, this week's lectures. So let's say, uh, let's write it like this: the temperature at which an electron occupies an energy state is energy state 0 0.1 eV above the Fermi level with a probability of 0.01 is approximately how much Kelvin. So we need to find the temperature at which the electron occupies the energy state 0 0.1 eV above the Fermi level with a probability of 0.01. So what would be the temperature? I guess everyone can take 2 3 minutes and then we can discuss the solution and those things. Just a second. Maybe let me write the, this was Fe equals to 1 minus 1 plus e to the power e minus ef divided by kt. So from this, try to solve this. We have got the difference between E and EF, that is the energy state is already zero point 0.1 eV above the Fermi level. We have got the probability, that is 0.01. So we have to just find the value of temperature. As like from previous discussion, we know that if T is constant, if E becomes constant as well. Try to solve this. You have to just put the values here. So maybe I'll explain this. So the, as it has said that the energy state is already 0 point, energy state is EF minus 0.1 EV, right? So that is E minus EF is 0 point, I guess, no, above this, right? So this is 1 EV, okay? And we have also got the value of K and those things, everything is there. So from this we can write it as like this. So this would be 0.01 equals to, as we know the probability is 252.6. Let's see, 252.6. Okay. So from this we can write it like this, 1 divided by 1 plus e to the power of 0.1 divided by kt. Just a second, let me get my calculator. Yeah. So the value of this is 0.1. So it is nothing but, let's say, make it 100, that is 1 plus e to the power of 0.1 by kt, or e to the power 0.1 by kt equals to 99, or kt equals to 0.1 divided by ln of ln, just a second, ln of 99, that is 4.595, or 0, just a second, 0.1 divided by 4.595 is 0.02176. From this we can write T equals to, mm, let's just make it like this, 253 kelvins. So what was the answer you have got? It was 252.6. Yeah. So it may be the correct answer because like I have used approximation. So it can be like this. Okay. So at 253, nearly 253 Kelvin, that like there would be an electron in the energy state that is above like zero point 0.1 eV, above the Fermi level, that is the EF values. Okay. So we'll move towards the next question. That is question number 2. So question number 2 was that in silicon, Semiconductor.
So once again, can you explain the first sum?
Yeah, sure. So here we have got that the energy state, that is the E. Just a second. Yes, so like let's say the energy state is E. So it's just above the Fermi level. So if it's the Fermi level, that is EF, the value between this is 0.1. So E minus EF comes out to be 0.1 here, as we have already written. So 0.1, and based on that, the probability of finding that electron in that energy state was 0.01. So if E is here, if E was 0.01 as well, just we have just calculated the value, that's it. From there we have just put the values here, and we have got this value, T equals to 253. So at the meaning of this is that at 253 Kelvin, the if like the probability of finding an electron in the energy state that is above the Fermi level by zero point 0.1 eV is 0.01. That is, there is a 1% chance that we can find the electron there. That's it. Is it okay?
Okay, sir. Thank you, sir.
Yeah, sure. Now, so in a in a silicon semiconductor that is doped with 5 times this per centimeter cube phosphorus atoms at a temperature of 300 Kelvin. Okay. Now, if the intrinsic carrier concentration, that is Ni, is 1.5 times 10 to the power 10 centimeter cube. So in general, the value of Ni ranges between 1 into 10 to the power 10 to 1.5 into 10 to the power 10. So if there is a problem that it doesn't like mentions the value of this, so you can write it as 10 to the power 10 or 1.5 into 10 to the power 10 as well. So let's say if this, find the electron concentration. Okay, and based on this there are several things, that the position of the Fermi level is relative to the intrinsic Fermi level, EFI is how much EV. So the next part, so this was the next part, and this was the first part. So the first part requires us to calculate the value of electron concentration, that is the value of N. So we need to calculate the value of N here, and here we need to get the value of the basic relation between, so that is the ratio of EF with EFI. We need to get this, and we have the we have already got that intrinsic carrier concentration, that is Ni is 1.5 into 10 to the power 10 per centimeter cube, and also we have got the dopant concentration, that is 5 into 10 to the power 16 per centimeter cube. So try to solve this. So invisible N and EF minus I. So we have to solve it like two different types. So the first one we need to find what is N, and in the second one we need to find the ratio of EF with EFI. Just check the numbers Ni and Nd. How much difference is between them? Maybe I'll explain this. So here we can clearly check that Nd is much greater than the Ni values here. So based on that we can consider and also at 300 Kelvin as well. So based on this we can consider a full ionization. So the value of N, that is the value of electron concentration, would be nothing but the value of Nd, that is the dopant concentration, or 5 into 10 to the power of minus 16 centimeter minus 3. So this would be the value of electron concentration. So what about the second part? We have here learned about the formula, I guess, here in this page. Maybe I'll write it here. So to get this, we know that n equals to ni e to the power of. Has someone done this already? No. Okay. E to the power of ef minus ef of I divided by kt. Right? Yeah. So was the values in case of extrinsic semiconductor. You have to directly put the values here. So we have already got the value of n. We have already got the value of ni. We have already got the value of k and t is already given as t is already 300 Kelvin. So we can directly get the value of EF and EFI. Try to get the answer. In the meantime, maybe I'll use a calculator to get the answer as well. So to solve this, it's better to get the value from here as well. So n divided by ni, we can get this value, that is 5 into 10 to the power minus 16 centimeter cube inverse, and ni was also given in centimeter cube inverse, so we don't have to worry about the units. The value would be 5 by 1.5. Sorry, 5 by 1.5. So this is nothing but 3.33 into 10 to the power 6. This was the ratio of this. We can put directly this value to the right side of this equation. So it would look like this: Ni by Ni equals to e to the power of Ef minus Ef of I divided by Kt, or we can write it like this: Ef minus EFI equals to Kt multiplied by ln of n by Ni. So this is nothing but 0.026 and ln of 3.33 multiplied by 10 to the power 6. So the value would be ln of ln of 3.33 into 10 to the power 6. So the values are 0.026 into 15.018 multiplied by 0.026. The values of these are E f minus E f of I equals to 0.39, right? Yeah, 0.39, or we can write it like this. So the basic question was that position of the formula relative to, so we can we don't need to do it like this maybe. So we can write it like this as well. So the value of EF minus EFI. So this is the value. So the answer is nothing but EF equals to 0.39. It will be in EV plus EFI. So the value of this new Fermi level is like 0.39 EV above the intrinsic Fermi level. So the Fermi level is situated 0.39 volt above the intrinsic Fermi level. Okay. So is there any question about this? If there is not, then I'll move towards question number 3. Yeah. So in question number 3, that just a second. At absolute zero temperature, the Fermi function for energy states below Fermi level is how much? So the question is, at absolute zero temperature, that is 0 Kelvin, the Fermi function for energy states below Fermi level is how much? So we have to first write the Fermi Dirac statistics. So based on this, we can get the values divided by kT. So try to solve this. And it has written that at 0 Kelvin. So at 0 Kelvin, what will be the changes in this function? And based on that, like how much will be the value of E? So at 0 Kelvin, what will happen? Just a second. 0, yeah. So you are saying that the formula for energy states below Fermi level is how much? So the probability is 0, right? You are saying that? Actually, like at 0, what would happen that it is less than EF. So based on that, if the value is like, let's say here, if E would be 1 by 1 plus, when the below 1 is 0, so what will happen that e to the power E of EF by KT, or we can say it as like E minus EF by 0. So this is e to the power infinite. That is 0 actually. That is not exactly 0, so that will like that is tends towards 0. And based on that, so if we can write it like this, so the value of if it would be 1, not 0. It would be 1. Okay, so we'll move on to the next one, I guess. So question number 4. So we'll move we'll take more like numerical problems, I guess, and based on that we can
Sir, could you please
yeah.
show the previous question number three, please?
Yeah, sure.
Yeah, thank you.
I'll share the videos and also the like the slides. So if you are solving the question at the same time when I'm asking the question, then you can write it on the paper. Otherwise, you will get the notes directly.
Okay, thank you, sir. Thank you.
Yeah. So let's move on to the next one. So there is a silicon wafer that is doped with 10 to the power 16 centimeter minus 3 argon atoms. Okay. The donor level ED is located at 54 millielectron volt below the conduction band. What percent of the donor atoms are ionized at the temperature T equals to 77 Kelvin? And they have already given that the value of NC at 77 Kelvin is 4.2 into 10 to the power 18 centimeter minus 3, and also the degeneracy factor of donors are 2. So to simplify, maybe I'll simplify it a bit. So we have the degeneracy factor as 2. So let's write it down like this. So the dopant concentration is 10 to the power 16 per centimeter cube, and we have got what we have got ED, ED values of 0.054 EV, and we have the it's located below CB. Okay, so it is below CB. So the CB minus this is that. So how to write this? Let's not write it like this then. And degeneracy factor G equals to 2, and we have got NC at 77 Kelvin as 4.2 into 10 to the power 18 centimeter per centimeter cube, and we have got No, apart from this, everything is there. That the donor level is located 54 milli electron volts, that is 0.054 electron volts below the CV, that is the conduction band. So we have got the conduction band concentration as well. So NC we have got here. So try to solve this and get what percentage of the donor atoms are ionized. So actually we need to get this. So N is to N. So they have written it like this. So N is to ND. We need to get this to get the percentage. That is the ratio between the electron concentration and the donor concentration. Also, we can, I guess, write it like this as well. So ED situated 54 MeV, but we can write it like 0.054 EV. The best option to start is towards this. So to solve this, best is to get the value of the electron concentration first. So that is nothing but this multiplied by Ne to the power of minus Ec minus Ef divided by Kt. From this, you have to calculate the values. And there is another one, that is the Nd plus, and it is nothing but divided by Nd 1 plus G of e to the power of Ef minus Ed divided by Kt. And here comes the degeneracy factor. So value of G is there. So you have to solve these two equations and you have to get get the values. And also another important one is that uh, to make the semiconductor charge neutral, the value of n should be also equals to nd plus. So these two terms, the first term here and the second term here, should be equal. So you have to solve this and you will get the value of n by nd plus. N by nd, not nd plus. Sorry, n by nd. What is G? G is the degeneracy factor. That is 2. So here they have written this. The degeneracy factor of donors are 2. So we have got the value of G here. The degeneracy factor, that is 2. Just get the answer and then I'll also solve this equation and then we'll check the if my answer is also correct or not. Yes, I can solve this equation. I'll not put the values here, but let's solve this one. 1 plus G of, from this what we can get is that No, I guess we have to solve it first. Sorry. How ND plus having those values are generated? ND plus having those values, which values are, you can turn on your mic and then ask me the question, then I will be able to like answer you correctly. You have the value of ED, right? And you have the value of EC as well. So you have to substitute some kind of a value here. Maybe I'll just simplify this. Just a second. So let's simplify this one as well. So to simplify this, we can get this as ln of n by ni equals to EF minus EC divided by KT, right? So we can write it as like EF equals to EC, and this will go towards plus KT. Just a second. EF goes outside. The value is minus EF plus EF. So EC plus KT of ln of Ni by N, right? KT goes here. No. Sorry. I mistaken. EF equals to KT multiplied by ln of N by Ni. N by Ni. Ln of this. So there was this minus term. And this should be N by Ni. Now you can substitute the value of EF in the second equation. So we have got this from the first equation. Just substitute it to the second equation. Maybe I'll do this. So what we have already got is N equals to ND plus equals to ND divided by 1 plus GEF minus ED by KT. From this we can write it as ND divided by 1 plus. Now we have the value of EF here. So we can write it as G multiplied by E of ED. So we can write it as N by NC. So we can write it as N by N of C e to the power of ED divided by KT. And from that we can write it as, let's write it as like this, ND, and it goes to the left. And so the values would be N plus, no, 1 plus G of N by NC e to the power of ED divided by KT, or N plus G by NC into N square e to the power of ED by KT. Now if we put the values here, putting the values, these were like, this would be ND was how much? ND was 10 to the power 16 centimeter cube, and let's remove this, I guess. Okay, equals to N, just N, plus G was 2 divided by NC. NC was 4.2 into 10 to the power of 18 N square e to the power of 0.054 EV divided by KT. Okay, so and the value of KT is nothing but 0.006636 EVs. So from that, if we put it into the calculator, just a second, 0 0.054 divided by 0.006636. This would be like this. E to the power of the same. Let's write it as 8.137. So e to the power of 8.137 is nothing but n plus 2 by 4.2 into 10 to the power 18 n square multiplied by 3418.64. Okay, and we get it as this. So multiplied by 2 divided by 4.2. So 1622 uh, into 10 to the power minus of 16 n square. So this is the value of this we have got. So it looks like an quadratic equation. So we can put it like this: 1622 into 10 to the power minus 18 n squared plus n minus 10 to the power 16 equals to 0. So based on this, we can solve this equation as minus 1 plus minus root over of 1 square plus 4 times 1622 10 to the power of minus 18 multiplied by 10 to the power of 16. Sorry, delete this area. What the heck? So this would be 10 to the power of 16 whole divided by 2 into a, that is 1.1622 10 to the power of minus 18. So now in this case, we know that like carrier concentration is a real number. So we just need to get the root is positive. So from this we can write it as like n equals to minus 1 plus minus. Let's calculate this thing. So it's nothing but 4 into 1622 into 10 to the power minus 2. So it's 64.88. So root over of 64.88 is nothing but minus 1 plus minus 8.12 nearly, and this one is 2 into 1622 into 10 to the power of minus 18. So this is 3.244 into 10 to the power minus 15. So the value would be, so in case of, no. So as it is a real number, so what would happen is that n equals to, sorry, 7.12 divided by 3.244 into 10 to the power minus 15. So 7.12 by 3.244. So it would be 2.1948 into 10 to the power of 15 per centimeter cube. Now the question asked for the what percent of the donor atoms are ionized. So this is the total number of ionized atoms. So we need to get the value of n divided by nd, and it was 2.1958 into 10 to the power 15 divided by 10 to the power of 16. That is nothing but 21.948, and it would be in percentage. So let's write it like nearly 22%. So the nearly 22% of the total, the total atom would be ionized. So like the carrier concentration would be like this. If anyone have any question in this question, so ask me. Otherwise, we'll move to the next one.
So could
20.
you explain from the quadratic equation solving?
Yeah, so like from the quadratic equation solving, so up until now you have got this, right? So this one you have got. From that, the basic, we are finding the roots. So minus b plus minus root over b squared plus 4ac divided by 2a. So this is the basic formula of solving the quadratic equation. And from that, we have just
So,
gotten, yeah.
so in that I have got n plus 1627.92 instead of 1622.
Where? So in this value. So there may be a
I
minor miscalculation. Just let me recheck. So you have got in the quadratic equation as
uh 1627.92 into 10 to the power of minus 18
1627,
n square
1627 point,
0.92
okay, into 10 to the power.
10 to the power minus 18.
Okay, so like I have then just a second. Let me multiply it. 3418.54 divided by 4.2 into 2. Yes, so there was a miscalculation. So this one would be 1628, right? So as we are
Yes,
taking
sir.
the as we are taking the approximation, because otherwise the like anyways we are taking approximation here as well, then we are taking several approximation here and there, so we are just taking the whole number because to it would be easier to solve the quadratic equation. So here we'll change it to 1628, and this one as well to 1628, right? So let's multiply it again. 1628 into 10 to the power of minus 2, 65.4. So 66.12. 66.12. So the value here comes out to be 8.13. And the below one is 1628 multiplied by 2. So 3.256. So the values would be, this one would be 7.13 and this one would be 3.256. So 7.13 divided by 3.256 is 2.1898, and here as well, so it would be 2.1898, and this one would be same 2.1898. So this is the answer would be 21.9%. So you've got this answer, right?
Yes, sir.
Yeah, that's fine. So as we are taking so much approximation and there may be some miscalculations as well. So let's, okay, so this one will be different as well. Na? This should be same as this. So this is the corrected calculation for this. So I guess if there are no more questions, then we can move on to the next one. So what would be the question number? This would be the question number 5. Are there any questions about this problem? Because this is the like the longest problem we like I had in mind. So if you have any questions, please go ahead. Uh, I guess there are no questions. So let's move on to the next one. So we have a semiconductor at 300 Kelvin, which has a doping concentration of Nd 2 multiplied by 10 to the power of 10 centimeter minus 3, and it has a intrinsic concentration of 10 to the power 10 centimeter minus 3. Find the number of holes at room temperature. So we have to find the number of holes, that is the hole concentration in room temperature. You can find it easily. Try to solve this and like tell me the answer as well. This will also like comes like this, there will be an also an quadratic equation in this case. So there are two major factors, we have to think about that two factors, and by combining those two equations we'll get another quadratic equation, and we have to take another again the positive of the roots, and then we'll find the number of holes here. Just take 2 minutes to solve this. I'll have some water by the time. So was anyone able to like solve this? If not, then I'll give you some hints maybe. So the basic thing we know is NP equals to Ni squared. So this is the first condition I was talking about. And the second condition is based on charge neutrality. So based on charge neutrality, what we have is that Nd plus P, it should be equals to N as well. So we have two equations here, and based on these two equations we can have an like equation. So like here we can write it as this. So this should be n equals to nd, we have got the value of this 10 to the power 10 plus p. So we have got this, and in this case we have got the value of ni square, so that is 10 to the power 10 whole square equals to n multiplied by p. And in case of n we can substitute this, so we can write it like this, multiplied by p. So we can have p square plus 2 into 10 to the power of 10 of p minus of 10 to the power of 20 equals to 0. Now we have to solve this equation and we'll get the values. So just solve the equation and tell me the values. And the solution is nothing but this, right? Minus p. And in this case, we'll consider only the positive one as well. maybe I should solve this. So the value of this would be 2 into 10 to the power of 10 plus minus root over of 4 into 10 to the power of 20 min. Okay, so this would be plus again 10 to the power 20. So these term is know what do we saying, and the value of this would be, so this would be 8 into 10 to the power of 20, and the value of that would be, let's write it down first. So this would be plus root over of 8 into 10 to the power of 20 whole divided by the value of 2. So we are considering the positive as p is a real number. Okay, so the we can get the value of p as, just where is my calculator, root over 8. So this would be minus 10 to the power of 10 plus 2.828 into 10 to the power of 10, right? Minus b plus minus root over b square minus 4ac. Just a second. Sorry. 4ac, right? 2a. Oh no, this is 2 anyways. So, so the value would be 1.828 into 10 to the power of 10 per centimeter cube, right? So the value is this. Please recheck this value. I guess there is some miscalculation from my side, but I'm not able to find that. But uh, I have done some miscalculation somewhere. Oh, okay, okay. I got this. Root over 8 was, so this was, and this one would be divided by 2 as well. So the value would be 2.828 divided by 2, 1.414. So this one should be 0.414, or we can write it like 4.14 into 10 to the power of 9 per centimeter cube. Hmm, let me recheck it again. It's fine, I guess. So this is the answer. So the number of holes at room temperature we can find is this. That is the hole concentration. So anyone have any question on this? Or otherwise we'll move towards the next one.
So why we can't solve this sum as the previous sum we have solved?
Which one? So like this
So
one?
for no, so in the sum which we have considered that n is equal to nd, since we have considered it as an ionized.
No, no, no. In that case, so let me just explain this. Yeah. So there's a major confusion between this. So like in this case, so you are telling about this one, right? Where we considered n equals to nd.
Yes, sir.
Yeah. So in this case, what was the main motive of this? Because nd was much higher than ni, because nd had the values of 10 to the power of 16, whereas Ni has the values of 10 to the power of 10. So 10 to the power of 16 is much higher than the 10 to the power of 10 value. So that's why we can consider n equals to nd. But in this case, what happens is that, just a second, where is that? Yeah. So in this case, the value of nd is 10 to the power of 10, in the range of 10 to the power of 10, and Ni is in the range of 10 to the power of 10. So what happens in this case is that nd is nearly comparable to the value of Ni. So we can say that, then in that case we can say that n equals to nd, because it's only two times. So it is not obviously much greater than, right? it is obviously greater than Ni value, but it is not much greater than. So we can't neglect the value of Ni here. So that's why the
Okay,
value
sir.
is, so that's why the value looks like this, because it's in the comparable range. So you have to check this. If your ND, that is the doping concentration, is much higher than the intrinsic one, then you can neglect the value of Ni, that is the intrinsic one, and you can just take the value of the doping concentration. But in this case, you have to consider it like this, because those are comparable values in the same like range actually. So it's just two times more than the intrinsic concentration.
Okay, sir.
Yeah. So we'll move towards the next one. So this would be, I guess, number 6, right? Yeah. So we have two semiconductors, that is A and B, two semiconductors that have same effective DOSs. Okay. And both at the conduction band and valence band edges. So the effective DOSs are situated at the conduction band and the valence band edges for both the semiconductors A and B. Now the question is that A has a intrinsic carrier concentration of 1.5 into 10 to the power of 10, where B has 3.2 into 10 to the power of 7 centimeter minus 3, and this one is also centimeter minus 3 at 300 Kelvin. So what is the band gap of B if band gap of A is 1.12 eV? So what we have here is that we have the band gap, that is Eg of Eg of A, which is 1.12 eV, and we have the intrinsic carrier concentration, that is Ni of A, that is 1.5 into 10 to the power of 10 centimeter minus 3, and Ni of B, that is 3.2 into 10 to the power of 7 centimeter minus 3. Now we have to find out the value of Eg of B, that is this. Eg of B, we have to find it out. It's a very simple one, so like it will be easier to solve, I guess. Let's take 1 or 2 minutes and then you guys will solve this. If I give hints, then it would be too much easier. So let's take your time and then try to solve this. Try to do this. What is Ni of, let's write it like this, and Ni of B. Write it like this. Try to do this. And we also have the value of this, like 1.5 into 10 to the power 10 by 3.2 into 10 to the power 7. And what is the equation we can get from this? Maybe I'll have this here for intrinsic cases. Yeah. No. So where is that? Where is that? Yes, from this one you guys can get this. From NP and NI squared. I'll move to the question itself. Maybe I'll write it down. So this is NCNV divided by root over NCNV e to the power of minus EG of A divided by 2 kT and e to the power of minus Eg by B divided by 2 kT. So these two terms cancel out and we'll get the value of this e to the power of Ega minus obviously by 2 kT divided by e to the power of 2.38. Let me check that. Minus Eg of B by 2 kT. So from this what we can get is ln of Ni of A, Ni of B equals to the values are E of GB minus E of G of A divided by 2 kT. Okay. Now based on this we can write it as, should I put this values? No. Let me write it like this. So the values would be 2 kT multiplied by ln of Ni of A divided by Ni of B plus Eg of A. Now we can have the values of this. Oh, so based on the values of KT, the answer may differ a bit, but that's it. So KT and this is ln of NIA. NIA was 1.5 into 10 to the power of 10 divided by 3.2 into 10 to the power of 7 plus EGA was, I guess, how much was it? EGA 1.12. We'll move to the next one. So what was this? This was EGB. I'll just use this. 2 kT multiplied by ln of this 1.5 divided by 3.2 into 10 to the power of 3, 468.75. So we need to get ln of 468.75, that is multiplied by 6.15, exactly 6.15, sorry, plus 1.12. So if we put it as KT values, so in the previous problem we have used KT values of this. So I am putting exactly these values here. Multiplied by 2, multiplied by 6.15. So this is 0.0816 plus 1.12 plus 1.12. So the values are 1.2016 EV. Yes, how much you have got? 2.38. How come you have got 2.38? Have I done any miscalculation somewhere? 6.15 multiplied by 0.06636. So, no, no, no. This is wrong actually. So, this one would be 0.8612. Let me recheck it again. 6.15 multiplied by 2, 0.006636, right? 006636. No, the previous one was right actually. Yeah. So this one was right. Or was it wrong? 300 Kelvin, right? So if we multiply it with 300, 2.38. How come you have got these values? 2.38. Is there any miscalculation in my one or yours? I'm not sure. Mm,
Sir, I have got 1.1608.
1 point
1608.
1.16. So it's nearby to mine, right? So there may be
Yes,
based on the,
sir.
yeah, so based on the approximation, the values may change. Yes, so what was yours? I'll write it down here as well. 1.16.
08.
Okay, 08. So it's nearby to mine, so I'm guessing that it is the correct one. I'm not sure if there was a mistake on your side that it came out to be 2.38. So you can recheck your values again, and we'll move towards our last question of today's, is that if temperature is halved and effective mass of holes are doubled, so what would happen to the Fermi level? So this was the last part of like this week's lecture. So if we have, let me draw this. So our Fermi level is here. This is EF. This is energy. This is density of states. So based on increase in temperature, the temperature has been halved. So right now the TA, or the change temperature, let's say TC, is half of the earlier, that is the, let's say, initial temperature and the final temperature. So this has been halved, and the effective mass of holes, so this is the final one, is 2 times of the initial one. So if these are the two conditions, what would be the change in this Fermi level? Should it go upwards? Should it go downwards? Or based on the effective mass, what will be the changes and those things? Just tell me the basic things, like if we increase the temperature, what will happen? So maybe we'll discuss this out. So first, if let's say we decrease the temperature, if the temperature is decreased, what happens? That number of thermally uh, what I said, number of thermally excited electron in the conduction band also decreases, because we are giving it a like less temperature, so that's why the thermally excited electrons number decreases. And based on that, what happens, that the Fermi level moves towards the conductance band. So there would be a upward shift towards this. Okay, and the shift is also significant as well. And now what will happen, that if, and we also know this one as well, right? So EC plus EV by 2 plus 3B KT by 4 ln of MH star by ME star. So based on this equation, we can say that if we double the effective mass, so effective mass is doubled, so it is like increased. Let's say it has been increased. So based on this, what will happen, that number of holes in the valence band will increase as well. So based on the effective mass of the holes, the number of holes in the valence band will increase, and based on that, the Fermi level will move towards the valence band. So based on this effect, the valence band will move towards the Fermi level will move towards the valence band. Now we have to understand which one is the more powerful phenomena. So based on the change in the temperature, this is the more effective phenomena rather than this one. So the mean change towards will be towards this. So this is the mean shift that will be towards the conduction band, and right now the band may be like situated like here. So the band will be here after TF has been T halved and image star F has been double the time. So this is the basic concept, because with the change of temperature, the change of like thermally excited electrons changed in the conduction band, and based on the conduction band the Fermi level shifts more than the based on the number of holes in the valence band. So that's why the basic shift would be towards the upper side. Let's say if it changes with the 10 electron volt based on the temperature, there would be a change of 1 electron volt based on the effective mass. So the mean change will be towards 9 volts towards the conduction band. So this was a basic example of this, but the basic mean change would be towards this. So if there is a change in temperature, the effect would be much more important than the change in the mass, like the effective mass of the holes. If there was a change in effective mass of the electron, that would be another major factor that would shift the Fermi level as well. So if anyone have any questions, you can ask me right now. Otherwise, we'll end the session of today's. Anyone have any questions? So we'll end the session today, and let's meet on next Sunday around this time, that is from 7 to 9. Thank you for attending the session.
Thank you, sir.
Thank you.